I spent all weekend preparing tomorrow's test. It's going to be PowerPoint, but it's not going to be A and B version. I only have you sit one chair apart and then do it that way. I don't finish this PowerPoint, I'm not worried. I do want to get one thing. I want to get you familiar with the mnemonic called oil rig. And I want that to be clear, because that's a major helper if you understand. Like we say, this was oxidized, this is reduced. Oil rig explains what that means, and I'll tell you right now, when I was in school where you are, I didn't know about oil rig. And I missed probably a lot of answers to questions because I didn't know about oil rig. And I wish I had known, so I'm sure going to teach it. And the last thing if I get that far, I do want to show you exactly how a thing called ATP synthase works. A few minutes ago, I put on 3 pictures, which of course I didn't allude to in your outline at all, because they're brand spanking new. That show you, because I know in my mind, I'm better if I get a picture, I can know more. I'm better at pictures than like a ton of paragraphs. And if you give me both of them, that's even better. So I'm going to do both of them. What you see there, on this side, that graph is the light that's absorbed by chlorophyll. And if you notice up here, a lot of absorption going on. Here is reflection. If you reflect green light, that's why you're green. So actually, green light's not being used to make food for a plant. That's what's coming off the leaf. Now, the leaf doesn't look blue or purple because that light's being absorbed. That's driving the process. Now, on the other side, you see the red over there. Well, the pine out there and the magnolia, they appear green. Now, I'll tell you right now, though, you saw the springtime leaves, the fall leaves turning red. There are pigments in that leaf, even when it's green, that's using those other colors. But if you reflect red, then you're not using red. So when that leaf loses the chlorophyll and it becomes red, it's going to soon fall off because it's not making any more food. And where it's attached to the stem, that when it falls off, it's called abscission. And as long as there's food passing through there, then the thing stays strong. Once the leaf shuts down and the food stops being passed, well, anything, if you don't use it, you lose it, and the leaf falls off. A good rain, a good wind, you see leaves trickling down, and that's how it happens. I don't think you're ever going to find a green leaf on the ground. It's always brown, it's always red, always yellow. And that's a bird knocks it off. So the picture over there shows you why something is green. If you see red, like I see the red sweater on it, that color is the one bouncing off back to my eyes. Green's hitting it, being absorbed. Yellow's hitting it, being absorbed. What's coming off her sweater is that red color. That didn't get picked out. Now, if you're white, like Jacob has a white shirt on, everything is bouncing off. Everything's bouncing off. And if you have a dark outfit like you have on, everything's being absorbed. That'll be hotter than his. Outside in the cool weather, you'll be warmer than he is. If you have the same sweatshirts, same make, and yours is black and the neighbor's are white, you're going to be warmer because that's going to soak up more heat. And that's why a winter coat being black is the most effective color there is. A white winter coat might look pretty. It ain't worth the flip though for to keep you warm. It'll keep the wind off of you, of course. Now, alright, metabolism. Now it makes no sense what's called outthrow. But then again, metabolism, back then, they thought it was making things. If you're making things, you throw it off, right? You make it, throw it away, make it, throw it away. Well, later on we realized that it's also breaking things down. So, as far as your outline goes, metabolism is now the sum total of all the chemical reactions going on. And I told you earlier, if it's a reaction that's making something, we call it anabolism. If the reaction is breaking something down like digestion, we call that catabolism. That's all under one big umbrella called metabolism. And the processes, if you grow and reproduce, that's got to be done by anabolism. Maintain structures, that's the anabolism. Respond to an environment to move. Nowhere did I mention breakdown of food. And I should have, because that's the other half, breakdown of... When your blood cells finally run their course and it's time to die, they must be broken down and got rid of. That's also a form of, but that's catabolism. And I should have listed a D, and actually that's what I read, and I wasn't thinking about. That's all anabolism right there. And so I wish I had, and I'm going to add to my slideshow for next quarter, to include a D and an E, and maybe even F, showing you breaking down things. Because that's just showing you the half that's building stuff. All right? Well, I just did this for you, so nothing should be news there. I think we've heard this before today's slide anyway, though. This is not news to anybody, but I believe in reteaching things until it finally sinks in. So, catabolism, and I think of a catastrophe. Because a catastrophe tears your life, tears you up. So, but I don't think that's bad, though. Because if you don't break down food, you're not going to survive. That's catabolism. You got to have it going on to use the food you eat. And then anabolism, well, when you break down that substance, you get out the energy. But when you build it, you put in the energy. So anabolism is always using energy to build something. Plants do it out there, and they build stuff like the black-eyed peas you eat, the corn you eat, the lettuce you eat, the carrots you eat. All of that stuff is made by the plant for itself. But it got no say of me eating an apple, and I'll get from the apple what the plant put in there. I can't make my own food, so thank goodness there's plants doing it for me. I said, well, I eat cows. Guess what cows eat? Plants, grass. So you can't get away from the fact that we need grass, we need plants. Not only do they make the food you eat, they give off the oxygen that you breathe. So if you remove plants from the earth, and that's what happened back when they say the dinosaurs, were killed a long time ago. They say that a meteor smacked into the earth. And like if you drop a rock in a dry creek bed, dust goes flying up, right? Well, the meteor smacked the earth and made so much dust go flying up that the dust was like a real heavy cloud and the plants perished. But the plants perished, who's going to go next? The animals. Now, some of the things didn't perish though. The ginkgo tree that we see, it survived all that crap. Its line is still here. And that's the only line that goes back that far in time. Only the ginkgo. And I need to buy me one. Because that tree is, boy, it's like trivia. That thing is just, there's no line like the Tef line. We don't go back very far. I don't know how far we go back in time. Maybe 1800s. I don't know where. I know Tifton, it used to be the word Tef, and Taft was Teft, and they've changed the name over time. So I can't trace my roots back very far, but a ginkgo tree can go back to before the dinosaurs. There's nothing. That pine tree can't go back that far. Oak tree can't go back that far. Some ferns can, though. Now, there's some ferns that were living right there with the dinosaurs with the ginkgo there. And there are a lot of things that are extinct. We find their impressions, fossils of, oh, look at this thing here. It's weird. The pterodactyl, with that weird flying bird. I think it's scary to get someone, but I would not want to get it. All right. So anabolism is building, catabolism is breaking down. Enzymes, which you've got to have enzymes or you will not live. There are enzymes in your brain that make your brain work. Well, a high fever, what's it called when you break down an enzyme? What's that called? It's a D word.
Denature?
Denature. A high temperature can denature enzymes. And if you take the enzyme in your brain and you denature them, your brain ceases and you die. That's what a high fever kills you. It destroys the enzymes that were keeping you alive. When the enzymes are gone, then you're right behind them, buddy. Enzyme, now, for a reaction to, for example, if this is going to burn, what reaction must start? Oxygen must be combined with the product right now.
Yeah.
When the oxygen runs out, we're having a fire.
It's gonna
It
die.
goes out. Now, if there's no oxygen, will the fire even start?
No.
Now, how can you make this burst into flames? Could you go to the heart? Get enough friction?
Maybe.
Like in your attic?
Maybe.
How hot you get in your attic? Everybody store old textbooks up there? Like I do.
Oh.
I took mine down. Because you know how hot it gets up there, and I don't want a fire starting in those textbooks. And if you have any kind of equipment, you used to have oil base, like you might store an old printing press that your father had. That's like a busting flames, and that's called spontaneous what? Combustion. And their fires will start for no apparent reason. There's no wiring problem, just boof. On vacation, come back, now you see smoldering ruins. Now, if I want to make a thing start on fire, what do I normally do to it?
Like
A match. Now, this match is a catalyst. It provides the energy now to make it start. If this thing in my attic sitting there, how long would it take before it bursts into flames? A long time, right? It'll happen by itself, won't it? Before it happen right now, I've got to input energy, don't I? And that flame is energy I put in here. Well, now, I had fried eggs for this morning breakfast. Now, without my enzymes, how long would it take me to break those eggs down and use them properly?
Long
I'd
time.
probably die first from starvation. I wouldn't break them down. But with my enzymes, how fast can I break them down?
Very fast.
A few hours. Enzymes, there are some reactions that require the input of energy to make them go. Like the match. Don't use it. I can take a magnifying glass and make a point, right? What's faster, the match or the magnifying glass?
The match.
I know it's faster, the magnifying glass or my attic?
The magnifying glass?
Yeah, it's faster than the attic, right? So these enzymes that most of your reactions would take too long to happen to keep you alive. But your enzymes, that's the match. They give the startup energy that makes the reaction go. And that's all there is to the enzyme. Now, does the enzyme get used up in the reaction? No,
it doesn't.
All it does is start it.
It doesn't involve.
I mean, if you're pushing a kid on a swing, you're the enzyme. You're not swinging though, are you? Now, if you walk away, what's going to happen to the kid? It'll stop. So, if you lose your enzymes, your life is going to stop. Okay? Enzymes are catalysts, and all they do, that's the match. They allow things to happen fast and efficiently. Now, enzymes, do they always break down or can they build?
They can build.
They can also build. Enzymes can take glucose and fructose and provide the energy to glue them together and make sucrose. Other enzymes can take sucrose, provide the power to separate them. Those are both enzymes. One's a catalytic kind of enzyme, and if you're catalytic, are you making or separating?
Yeah.
Separating. If you're anabolic, you're making or separating.
Yeah, building.
So if you take an anabolic steroids, you're making bigger muscles. Okay? Yes.
I forget, but are enzymes like specific?
Oh man, yeah.
Okay.
Like the one that breaks down sucrose is the one that's called sucrase.
Okay.
Yeah, trypsin breaks down protein. It won't do nothing to carbohydrate.
Okay.
So they're all, that's a lock and key model that we're talking about.
Okay.
One key, one lock. So if you have 1,000 reactions going on, then you have 1,000 hormones enzymes controlling. One per. And if you can't break down milk because you're lactose intolerant, then you cannot make lactase. And the acid builds up in your body. So you find some milk substitute. So there are some folks who are missing enzymes. They don't kill them, but it does alter the way of life, though. All right. You ever wonder, and I've wondered this, you might not, I've seen deer in the woods eating mushrooms. Would you do that? Ain't no way I'm going to chow down on mushrooms. Why would I kill that deer?
Aren't there some good mushrooms though?
Oh, there are, but I don't know what they are. I mean, it'd be Russian roulette for me to take mushrooms. Now, I don't know whether they're more good or bad out there. I don't know anything about mushrooms except if I want mushrooms, I want to Winn-Dixie about it.
Yeah.
That way I know what I'm saying. And if somebody says, I had a person in college, he's a professor, he would go out and pick mushrooms, come in and cook them. I wouldn't eat them. Because he would go out and he said, well, if you look at this and this, and I'm going, they'll look like me, but they all look, he said, well, you got to look at this. And I said, well, I can't see what you're seeing, doc. So I just had me a boiled peanut. But he would do that, saute them, and some folks ate them. But I never tried to impress anybody. I was frankly scared of it. But no, I ain't going there. My mom always told me, don't ever eat mushrooms. After a long time, I wouldn't eat them even when they see. I was so scared of it. But my wife cooked mushrooms in the thing it's a casserole she makes for the springs, put mushrooms. I didn't know it. I ate them. These things are pretty good. To me, they have no taste. So if you didn't have them, I don't know what I'd miss, but I know I like them that way. And when I get a steak, I want my mushrooms on the side. Yeah, it just adds to it for me. But anyway, hydrogen sulfide is a deadly gas. Yet some bacteria got to have it to live. It'll kill you though. Your metabolism does not use that gas, theirs does. Apparently, deer have evolved a kind of metabolism. He can eat. Could you eat what a buzzard eats?
No.
Ain't no way. I wouldn't want to eat it. But that stuff is poison. It's rotten. Yeah, no, I'll tell you what though. When these buzzards though, can you imagine what happened if everything ever died and still here now on the roadside? You call out here thinking. So we need all these things, and the bacteria. I mean, I think of a buzzard, and of course it gets a lot of shooting one. I want to shoot anyway, but they clean the environment up. But they eat things that would kill you. Their metabolism is what makes the difference. All right. Now here's the oil rig. I've been waiting to get here. This is something that I've learned new, and I wish I knew it when I was in school. We're going to talk about energy transformations. And this is why I said, let's stop the show for a minute and let me insert some slides about a thing called oil rig. And like I said, I wish I knew that when I was in school. They thought I was a genius instead of idiot. Okay, a mnemonic is like, ever heard of one called KISS?
Keep it simple, stupid.
Yeah, in Army they taught us to keep it simple, stupid. If you give an op order for a battle plan, you don't want to give too much information because when you're over, folks going, what do you say? So they always tell the officers, kiss it, keep it simple, stupid. That's a mnemonic, and I use it even in teaching. I try to go too deep sometimes because if you don't keep it simple, you'll never get that ship off the ground. All right, oil rig. Let's talk about that. All right. Oil, oxidation. O is loss. And I've even shortened it to oxidation loses. I just said loses electrons. Oxidation loses. I'm going to check my PowerPoint when they say that. That's why I copied off some of the website. But I want to make mine change. I want to say oxidation loses electrons. But if you look at it there, the O stands for what? I stands for nothing at all. L stands for loses electrons. The I just makes the word make sense. I mean, L wouldn't make it work. Oil rig. So oxidation, any chemical that loses electrons is oxidized. That's a catabolic reaction, right? If you lose something. So anytime a chemical loses electrons, we say it is oxidized. The next one, I didn't understand for a long time. If I say to reduce something, do you add or take away from it?
Take away.
Now look right there, it says there.
Gain.
Gain, I couldn't, gain, how do we get gain from reduction? And then it hit me. I know how it now. Reduction is gain of electrons. Now here's how it works, okay. Let's pretend, oxygen is a -2. You know that, right? That's in the I'm going to say oxygen -2 now. Oxygen -2. Who is more positive? A -1 or a -2? Who's more positive?
-1.
The one's closer to zero. Now, if oxygen, which is -2, all right? Let me back it up. I went the wrong way. Let's go with because sodium is going to be reduced. Sodium is +1, right? Sodium is +1. Okay? If you give sodium an electron, does it become +2 or plus nothing? Why not? Why not? Sodium is +1. All right, +1. I give him an electron. What electrons?
-1.
Well, if you're +1 and I give you -1, what's your answer? You're nothing.
You neutralize.
So, did you become less than you were?
Yes.
That's
Be
the reduction
reduced.
part.
Okay.
That's the reduction part.
Okay.
Sodium, after it gains an electron, is he not less positive?
It is.
That's the reduction. I gave you the electron. That's not the reduction part. And giving you the electron, I lowered your positivity. You're no longer +1. You're nothing. Is that not lowering something? That's the reduction part. See, in my mind, I was trying to figure out how in the world can I give you something and say I'm reducing you. I go, that makes no sense at all. And finally, I reckon because I'm 61 years old and I understand more now, I said, wait a minute. If you reduce sodium, he was +1 before I reduced him. I give him the electron. He is now plus nothing. I lowered his plus charge, didn't I? I reduced his charge. And now I understand how gaining the electron can reduce something. It's not the electron, it's the charge that's being reduced. Now, oxidation works the very opposite. That's going the other direction. That could be called addition, really, but it's not oxidation. The main thing, usually we oxidize oxygen. You remove electrons from oxygen and you use them somewhere else. So if you're losing electrons and you lose it most often from oxygen, we just call it oxidation. You might lose them from fluoride because you lost electrons. If we use fluoride, we still call it oxidation though, because the big oxidizer is oxygen. So, but the rig part, I never understood until I guess maybe about a month ago when I was putting PowerPoint together. Because, like I said, I never could understand how you can reduce something and yet gain electrons. I think you're getting fatter. But then I realized that they're not discussing the electrons, it's charge they're talking about. I reduced the charge from +1 to nothing. That's what was reduced, and now it makes perfect sense to me. I wish I knew that back when I was where you were as a student. And I guess the professors back then didn't know it either, because they didn't mention reduction, and they didn't mention how something lost its charge by gaining electrons, but never did paint me the picture. I just painted y'all. So here's reduction. I'm gaining electrons. Now, if you look on this side, we have copper. He's a +2. I give him a negative. Is he still +2?
No.
What's he now?
+1.
Does plus become less? That's reduction. You went from +2 down to +1. And I don't write a 1 because the plus means you got 1. But that's what's meant by reduction. And the reduction part is he became less positive. I know I gave you the electron, but that made your plus nature drop. And because it dropped, that's why it's called reduction. It also if you're less positive, aren't you more negative? Can you be less positive, less negative too? No. If I can say this one right here, if you compare this one to this one, just those two, would you say this one is less positive than that one? Or could you say he is more negative than that one? I can say both ways. But I prefer to say less positive. I can see that there. I can see the +2 and +1. But I got to admit that I understand that if you're less positive, that means you're more negative. Because those go hand in hand. All right? Let's frame one. Now I'm just hitting it one more time. I'm just stressing that the reduction refers to the charge, not the addition of the electron. It's not about the electron, it's about the change in the charge, being reduced from +2 to +1. That's your reduction. And it's done by adding electrons. Now if you take electrons away, then you're becoming more positive, right? Would that be oxidation? An oil rig, now it works. Oil rig, oxidation loses. If you lose electrons, you become more positive or more negative. If you more positive. And rig means reduction is gain of electrons. If you gain electrons, you become more
Negative.
or less.
Positive.
There you go. Works beautiful now. I wish I knew it 30 years ago. God, it'd been so much easier. The electrons that you remember when you gain the electron. Now, if you gain it, that's a reduction, right? The electron you gain, that makes you an energy carrier. When you give it back up again, you will give off energy with it. Things that are reduced carry energy. The electron, their token, represents energy they can give to something else. You thought ATP was your energy source? There are other ones. ATP is your main one, but if I reduce you by giving you electrons, sometime you can give that electron back off, and out comes energy with it. That's the same thing ATP is doing, and you're going to find out there's a lot of that going on. And when we first teach biochemistry, it's always ATP, 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 ATP. And you start thinking it's only ATP. No, reduction, when I give you the electron, or two, that forms a bond when I give them to you. A bond forms. So I take them back off again, the bond's released, out comes energy. That's as good as ATP. And they use that, by the way, to make ATP. And I got a picture showing that later on too. Now here's oxidation. Now in oxidation you have something like iron, which before you fool with it, is a +2. Now if I remove an electron, why does it become +3?
Because it lost a negative charge.
It lost a negative charge, and now when we're positive, it shows itself. because you lost. Now, so iron, when you go from +2 to +3, are you not getting to be more positive? Ain't that more? Ain't 3 more than 2? But if you're more positive, guess what you also are? Less.
Less negative.
There you go. You're one way or the other one. So, when it went from the +2 to the +3, what had to happen? To win an electron. Now when he did that, he became less negative, more positive. Now, anything that loses electrons and becomes more positive, that's negative. That's oxidation. It usually happens to oxygen. And that's what we call it, oxidation, before we realize other things do it too. We kind of misnamed that bad boy because sulfur can do it, nitrogen can do it, all the others can do it, but we have never changed the name. I think the first one we ever studied doing it was oxygen. So we just simply called it oxidation. Then we went, oh crap, other ones do it too. So if you oxidize fluorine, or rig, OIL, loss. Well, if you lose electrons, you got to become more positive, right? And when something is oxidized, it gives off the energy. When I reduce you, I store the energy because you gained the electron, right? When I oxidize you and I pull it back off again, you release the energy. So one more time. Between oxidation and reduction, which one has the energy inside it that you can use? Reduction does. And which one doesn't have energy because it just gave it away?
Oxidation.
Oxidation. So if you take ATP and you release that phosphorus and you pour out the energy, is that more like oxidation or reduction?
What was the question?
If you take ATP and make it become ADP by losing, if you're losing something, would that be more like oxidation or reduction?
Oxidation.
Because you're losing. Oxidation. And if you lose, the moment you lose it, out comes energy. That can be used to make tears and make you walk. But now, when I want to put it back, like the mitochondria do, I want to put it back. Are you going to do oxidation or reduction?
Reduction.
I'm going to do reduction. I think you're starting to catch up. It took me for a year.
So energy stays inside, you gain it.
Okay, if you reduce something, are you giving it energy or taking it away from it? Because I'm adding electron to it. If I add electron, I'm adding energy. So if you reduce something, reduction is gain.